All right, let's just jump right in. Today, we're going to pull back the curtain on one of the biggest, highest stakes games happening in tech right now. How these top AI labs actually train those massive, world-changing AI models.
I mean, really think about that for a second. When a lab decides to train a new frontier model, they're basically pushing a button on a bet that costs hundreds of millions of dollars. It's a one-shot deal. If you get the initial settings wrong, poof, that money is just gone. So the question is, how on earth do they make this insane gamble predictable?
So here's the plan. We're going to start with the core problem they're all trying to solve. Then we'll look at the two big strategies they use. One that's all about keeping things stable, and another that's about predicting change. And finally, we'll cover a really clever shortcut that kind of makes the whole thing work.
Okay, so let's start with the problem itself. Before you can train any AI model, you have to tune a whole bunch of knobs and dials, right? These are called hyperparameters. They control stuff like how fast the model learns. Now, if you get those settings wrong on a huge model, you've just created a multi-million-dollar paperweight.
And what's wild is what happened right after ChatGPT blew up. It's like a switch flipped. The whole industry went dark. All these top labs, they just stopped publishing their secrets. Everything became super competitive. And that's exactly why these new, detailed papers from labs like DeepSeek and MiniCPM are such a big deal. They're giving us a rare peek into how this stuff actually gets done now.
So how do you solve this massive problem? Well, the answer is to create a kind of engineering recipe book, and that's exactly what scaling laws are. The idea is absolutely brilliant. You run a whole bunch of really small, cheap experiments. You find patterns in how the model behaves, and then you use those patterns, those laws, to write the perfect recipe for your final billion-dollar model.
Okay, so we've got this recipe book idea. How does it actually work? Well, the first major strategy is all about making the recipe dead simple. The goal here is to design your model in a very specific way, so that the best ingredients, the best settings, don't change no matter how big your model gets. And this whole philosophy has a name, Maximum Update Parameterization, or MUP for short. The logic is just so simple and powerful. If you can find the perfect learning rate on a tiny model that costs almost nothing to train, and you know for a fact that the exact same learning rate will work on your giant final model, well, you've just eliminated all the guesswork. You've made the problem stable.
So, what's the trick? How do they actually do it? This table shows you the secret sauce. While a standard model uses one single learning rate for everything, MUP does something totally different. It gives each individual layer of the neural network its own, carefully calculated learning rate. That's the key. That one change is what makes the whole system stable as it scales up.
And listen, this isn't just some weird academic theory. This is being used in the real world. Big players like Cerebras and MiniCPM use MUP, and we're even hearing that Meta is using their own version, something they call MetaPAP for Llama 4. The goal is always the same: make life easier by keeping your settings stable.
But that brings us to this really fascinating fork in the road. On one side, you have MUP, which says, let's change the model so the settings don't have to. But on the other side, you have a totally different way of thinking, led by labs like DeepSeek. Their approach is basically, why fight the change? Let's just predict it.
And that's our second big strategy. It fully embraces the idea that your best settings are going to change as the model gets bigger. So instead of trying to stop it, the DeepSeek approach is to measure that change with incredible precision and then just project it forward.
So how do they pull this off? Well, step one, they run what's called a grid search. They just run a ton of experiments on a bunch of different small models. They're trying out all sorts of learning rates and batch sizes, just gathering data points to see what works best at each small scale.
And then here comes the magic trick. You can see it right here. They take all those data points, the best settings for each small model, and they plot them on a graph. And what they find is a predictable trend. They can literally fit a line to that data. And that line, that scaling law, lets them predict with incredible accuracy what the perfect learning rate is going to be for their massive 67 billion parameter model. It's not about stability, it's about direct prediction.
Now, here's the thing. Whether you're in the stability camp or the prediction camp, you still have to run a lot of experiments to get your data, and that can still be pretty expensive. Which brings us to a really clever tool that these labs use to make it all affordable.
Okay, so here's the problem this shortcut solves. It's a little technical, but stick with me. Normally, when you train a model, the learning rate slowly goes down over time in a curve called a cosine schedule. But the shape of that curve is different depending on how long the training run is supposed to be. That means you can't just stop a long run early and pretend it was a short run.
The whole learning process would have been wrong. It's a huge pain. The solution is a different kind of schedule, and it's called WSD, Warm-up Stable Decay. And it's genius in its simplicity. You start by warming up the learning rate. Then, and this is the key part, you just hold it constant and high for most of the training. That's the stable phase. And only at the very, very end do you let it drop off.
And this is why WSD is a complete game changer. Because of that long, flat, stable phase, you can grab a snapshot of the model at any point during that phase, and it's a totally valid endpoint for a shorter training run. This means they can get all the data they need from just one single long run instead of dozens of separate ones. It saves an unbelievable amount of computer time and money.
All right, so let's tie this all together. What are the big things to remember? First, training these frontier models is a massive, high-stakes engineering puzzle. Second, to solve it, labs rely on a recipe book of scaling laws to make things predictable. Third, there are two main ways to write that recipe. Either you focus on stability using tools like MUP, or you focus on prediction like the DeepSeek team. And finally, none of this would even be possible without clever hacks like the WSD schedule to make the experiments cheap enough to run. And that kind of leaves us with one final huge question to think about. As these AI models get even more powerful and even more insanely expensive to build, is this secret recipe book, the knowledge of how to scale them predictably, is that going to become the most valuable, most important asset in all of AI?